Well, thank you for being here this evening. You're all at Akron Fossils and Science Center, right? You came to the right place? Well, we have one of our special guests that joins us from time to time as he's passing through America. And it's Ian Juby. Ian Juby is the director for the Canadian Creation Museum and also contributor to our museum here in Akron. Ian has done lectures here before. We absolutely love it when he comes through town. And he's made a great contribution to us in terms of our displays and so forth, and continues to do so. So tonight, Ian's going to talk about the Joggins in Nova Scotia and all of the evidence that he has found there that demonstrates catastrophe. So without further ado, we want to welcome Ian to the stage, and he's going to take it from here.
Okay. Thank you much.
Okay, well, let's get down to business. Tonight we're going to talk about the fossil cliffs of Joggins, Nova Scotia. Now there's the cliffs right there. They're huge cliffs. They're 80 to 100 feet, depending on where you are. And you'll notice how the rock layers are tilted to the south about 20 degrees. That's very convenient. And this area is the place of the highest tides in the world. Twice a day, the water, this is in the Bay of Fundy, the water in there, in that bay, goes up and down 50 feet twice a day. It's very impressive. During low tide, you can walk out almost a kilometer. It's about a half a mile at low tide. It's very, very impressive. And so the water continually coming up and back, combined with freeze-thaw, things like that, and general erosion, constantly erodes these cliffs back. So if you ever get the chance, you want to go to Joggins in Nova Scotia. I'll show you where it is in a second. But if you go there, don't hang out right there, okay? It's take a tip from old Ian. It's very, very dangerous. Bring a hard hat with you. It only takes one rock to kill you, okay? And there are rock falls constantly. Now the advantages are you see new fossils every single year, and I go back every year, and every year I learn something new. I have yet to go, and I've been going for years, and I have yet to go and not learn something. So it's famous for these fossil polystrate trees. Now the term polystrate comes from the word poly for many, straight for the rock strata. It cuts vertically through many strata. So you got the layers of rock here, and you got a fossil tree which has been buried through the rocks. Now these rock layers are supposed to have accumulated over millions of years. Well, wait a minute. Is that tree going to stick around for thousands or millions of years while it slowly gets buried? I don't think so. So right off the bat, you have a major problem to the idea of deep time. Now the conventional interpretation for these trees is that they were buried where they grew. In other words, this tree was growing in a swamp, and tides coming in and out over the years would slowly deposit sediments. I don't believe that for a second. I'm going to give you about a dozen reasons why I don't believe it, but I'll show you that in a second. Oh yes, Google Earth. Let me show you something real quick. It's actually not Google Earth. It's actually Whirlwind. Here is North America, and here's Canada. Here is, Nova Scotia. So this is Nova Scotia here, the province. And right up in here is the Bay of Fundy, and right in here is Joggins. So basically, when you come across the border from New Brunswick into Nova Scotia, hang a right, and it's right in there. There's actually signs going there and everything. What I'm going to show you is a rock layer that, although it's exposed along the cliffs here, that rock layer actually goes this way and actually outcrops way over here. It also outcrops over here in New Brunswick. Now the reason I show you all that is to give you an idea of just how big and how many fossil trees we're talking about here. Okay, at any given time when you walk along those cliffs, you can see 30 to 50 upright fossil trees at any given time. That layer then continues on all the way through here. It's all packed with fossil trees. We're talking hundreds of kilometers. So it's about 100 miles or so from there to there, give or take. So 100 miles, you can follow that layer and see countless fossil trees if you can find exposures of it. There's also coal seams, which were extensively mined throughout this whole area, especially over here, Point Tacony area. So I'm going to come back to presentations. Where did I leave off? Oh yeah, right here. Now, some of these trees are huge. And by the way, I should mention they're actually not trees. They're giant hollow reeds. And they're still around today. That plant grows in my backyard in Ontario. It gets about this tall. And you can compare the size of it. There's where the top of the plant was. You can see the trunk. But it goes in behind the mud here that was washing down the cliff. And there's the cavity left behind by the top of the tree. So that whole thing is cutting through about 30 feet of strata, roughly. Now, again, remember, this is a giant hollow reed. It's not a tree. So it's actually much more fragile than a tree. Now, again, coming to the conventional interpretation, how many people have heard of talk origins? 1, 2. Nobody's heard of talk origins. That's good. It's a bad site. Stay off it. Okay. Talk Origins is the anti-creationist encyclopedia on the internet. It's been around for decades. It's the authority on the anti-creationary, pro-evolutionary stand. And if you go to that website, they talk about the upright polystrate trees. They say, oh, well, it's not a problem for old Earth. It wasn't a problem back in the 1800s. It's not a problem now, because they grew in place. And they will show you this drawing, drawn by William Dawson, Canadian geologist, who, by the way, was a creationist. He is an old Earth creationist. He believed the Earth was old, but he also believed it was created. He was a theistic evolutionist. And so they kind of play that up. So they say here, even this creationist recognized that these were trees that were buried in situ. Well, this is the drawing they will show you. Now, notice there's the trunk there, the stump. Here's a root called a Stigmaria. I'm going to show you a close-up of that. Here's what the roots look like. They're called Stigmaria, and you can actually see this is the root itself, and you can see where it mates up to the rock, makes the mold in the rock. You can see that. And then you can see these black carbon marks. That is actually rootlets. So in all of these little pock marks, a rootlet radiates out from the root. Do you follow me there? Okay? So you got this root that's like this, and radiating it out in all directions are rootlets. Very important. So now, let's take a look again at William Dawson's drawing. He's got rootlets drawn all over the place. Do you see any attached to a root? Not a one. In fact, the one root he does have doesn't have any rootlets attached to it. What's going on there? This is evidence of burial in situ? No, I don't think so. This is evidence that this stump and all these rootlets have been ripped apart. They are polystrate rootlets. Why are they polystrate? I don't know. In fact, nobody does. I'm still trying to figure that out myself. What on earth made these trees get buried upright? It does happen in floods, but these ones seemed exceptionally prone to it. And to be honest, that's a research project. But the evolutionists don't have an answer either, because their in situ argument doesn't work. So the one root he has is clearly been stripped of its rootlets. There is no roots other than that one attached to the stump. Where'd all the roots go? The roots have been ripped off. This is evidence of a flood, of catastrophe, not evidence of deep time. Now, here is another Stigmarian root, still on the cliff. Look for yourself, no rootlets attached. In fact, I showed you this picture before. You recognize that, right? Let's take a close look at the roots on that trunk. Look at that. There's the root. You can see for yourself. Not a single rootlet attached. So yes, it has roots, but no rootlets. The rootlets have been stripped off from the roots. It is very evident this was not buried where it grew. It's very evident it was actually rooted up from the ground by something, most likely a flood, and then transported and reburied. It's obvious that's what happened. Now here's another one. I'm going to see if anybody can spot it. There's actually two stumps in that picture. Does anybody see the second one? And if you don't see it, don't worry. I walked by this for 3 days before I saw it, and I was looking at it with my own two eyes. Oh, Timmy thinks he sees it. Okay, let's walk through this. You can all see the first one, right? You're all trained experts now. Okay. first things first, let's take a look at the root. I'm going to come back to this, but notice the root goes down and then comes back up above what would have been ground level. See, the rock layers tilt this way, so ground level would have been about there. And yet the root doesn't go down, it also comes back up above what would have been ground level. It's a technical term, it's called a negative geotropism. Roots grow down, not down and up. That's evidence that they were buried while floating. Now, these ones did have rootlets, but immediately below that is another fossil root. You can actually see it there, and another small chunk right here, and they both come into the cavity left behind by another stump. Let's take a closer look at it. There's the root coming in, there's the cavity, there's the other root, and if you look real close, you can see the bark impression. One, you see the bark impression. That stump is buried upside down. Last I checked, trees don't grow upside down very well. I could be wrong, maybe. But last I checked, they don't grow upside down very well. This one has intact roots, and it was buried upside down. The roots are in the same layer as other roots. That's all supposed to be evidence that it was buried in situ, buried where it grew. Unless it was growing upside down, I don't think it is buried where it grew. Not too likely. Now, I just came back from Tennessee. This was a National Geographic photograph taken in 1975 in a coal mine in Tennessee. Now, in the National Geographic article, they said it cut through 30 feet of strata. They said it was in the Kettles coal mine, and it was near Cooksville, Tennessee. None of the above is true. Not even close. It cuts through 10 feet of strata. I know because I've personally gone to this tree. You'll see in a second. It was nowhere near Cooksville. It was near a town called Wartburg, and it was in the Pee Wee coal seam. So, here it is today, 35 years later. Same tree. A couple rocks have fallen out of the cliff now, but you can see when you compare the two side by side, even the stains in the bottom of the tree are the same. It's the same tree. Now, a consultant with the Creation Evidence Museum somehow, through an act of God, found this tree. I'm still going to talk to her and find out how she found it, because I went up there. I knew I had an idea where it was because I had been there once before, and I still got lost up there. It took me 2 hours to get back out of the bush and make a phone call to Neil to find out where I was going, okay? So it was really hard to find. The reason I went there is because there are all kinds of polystrate trees there. So the one I just showed you is actually just off to the right here. There's another one. There's another one. There's another one in here somewhere. Where to go? I'm looking at it on an angle here. Oh, there's one there. And that's one there. That's a small one. So there's actually several there. I found about a dozen large ones and about a dozen small calamites. This, by the way, is a fossil calamites. Still alive today. It's the horsetail, if you guys are familiar with it. That one's for you guys, by the way. That's for your museum, okay? These guys started a museum in their bedroom, so I'm sort of brought them some fossils for their museum. So that's a fossil calamites. So it's now at the Detweiler Museum of Ancient History or whatever, right? Okay. So the calamites, I found again another dozen or so. In that entire area, I did not find a single root, not one. And I went looking. Were they buried in situ? No, I don't think so, because the roots are gone completely. I couldn't find roots or rootlets, not a one, even though there was dozens of these all over the place. They were all stripped clean of the roots. Now, the reason I went there is Creation Evidence Museum, Dr. Carl Baugh, wanted a copy of the tree. So I went there, and I actually made a mold of the fossil tree. And it was a real chore. Boy, I didn't know what I was getting myself into, let me tell you. It was actually a mile hike on the side of a very steep mountain that's been heavily mined, so the whole side of the mountain is loose rock and vines and thorns and rattlesnakes. It was just really nasty. It was a mile hike carrying hundreds of pounds of stuff, including that ladder. I was by myself, so I'm climbing up this mountain, falling down the mountain, climbing up the mountain, anyway. So the reason it's pink is because it's painted with a paint-on silicone, rubber silicone. And it's a two-part silicone. You carry it in two parts, you mix it together, and the chemistry turns it into hard rubber. So while it's still soft, you actually paint it on as a very thick rubber layer, and then it dries. Later on, because this is just thick rubber, it's very floppy and soft and flexible, we then make what we call a mother mold. And in this case, I use plaster, just plaster of Paris, and burlap. It's the same stuff they use in dinosaurs. When they're removing dinosaurs, they make a plaster burlap jacket. Same stuff. And so I just break it into sections, so this has a flange, which I just separate with saran wrap, basically, while it sets. And then later on, we just peel those off. That makes up a solid shell. So basically, this preserves the detail, this preserves the general shape. You follow me so far? Okay. So then we get to take all this off, cut it all up into pieces, and backpack it out of there again. Oh, it's exciting. Yeah, took a long time. Anyway, this is it's covered in saran wrap right now because I'm about to start painting the styrofoam here. Unfortunately, I couldn't mold the cliff. The cliff turned out to be way more unstable than I realized, and I was afraid to do anything to it for fear that I'd pull the whole cliff down on myself and win the Darwin Award. So I just left it there. You can be assured I would have won the Darwin Award too. Oh yeah. We'd like to thank Ian Juby for removing his genes from the gene pool. I can see the headlines now. Anyway, so what we did is we got back to Creation Eminence Museum, cast the tree trunk. So that's a cast of the mold, done in fiberglass. So we had to hand sculpt the cliff. Now, what I want to point a couple things out to you here. This is a layer here. You see how it's bent like that? I'm going to show you that right, left, and center here today. That's very common with polystrate fossils. It's actually evidence for a powerful watery flow. It's called okay, you guys ready for a technical word? Are you taking notes? No, okay, smart man. Mental notes, right? Okay, there we go, good answer. Okay, it's called a vegetation-induced sedimentary structure. So it's a sedimentary structure or a layer that was induced by vegetation. In this case, an upright plant. And basically the water is flowing this direction. As it approaches the plant, it has to split and go around it. And just like water going over an airplane wing, the water going around the plant has to speed up because you have to jam more water around the plant in a smaller area, so the water goes faster. As a result, it scours the dirt on this side, actually picks it up. When it gets over to the other side, the water joining back together slows down, and so it drops the dirt. And so you wind up with a dip on this side and a pile on this side. Do you follow me there? Okay? Very common. You see this lots at Joggins. I'm going to show you as we go through the photographs. I won't even need to point it out to you. You'll see it. The other thing, and it's hard to see in this picture, but this layer is cross-bedded. See all those angled lines there? And if you were here for the last talk, I talked about that in our research at Glen Rose, right here at Creation Evidence Museum, where we produced crossbeds in a flume. Basically, as the water comes this way, it slows down, and as a result, it drops the sand just like a conveyor belt and makes a whole pile of angled planes called crossbedding. So there's the model itself. I couldn't finish it because of weather. I had to come up here for this talk and for this week, and so we just left it for now. I'm going to go back and finish it after I'm done here. Okay, you've seen now two supposed fossil forests, as they call them, okay? Joggins, Nova Scotia, and Wartburg, Tennessee. Let's head up into the Canadian High Arctic. This is Axel Heiberg Island. This is only 10 degrees from the North Pole, okay? Pretty cold there. It's nighttime for half the year. It's certainly not tropical, but you will find upright fossil stumps from tropical trees buried in the dirt. What are tropical trees doing in the North Pole? What an odd place. Now here's the other thing. These trees aren't actually fossilized, even though they're called a fossil tree. You can cut them with a handsaw, a wood saw. You can take tree ring samples. You can light it on fire. Supposed to be 45 million years old. Whoops. Yeah, whatever. There we go. They're supposed to be 45 million years old. So let's take a look at the tree rings. Now, this is tree rings from a modern tree in British Columbia, Canada. It's a similar tree. It's a redwood. This one up here is the tree rings from the Dawn redwood from Axel Heiberg, okay? So when you take a look at the rings, something very interesting to note here. Here's one ring, and here is another. So if you were to follow these around, this is a micro photo, these rings would actually go up and around in a big circle and then come back to here, okay? So you're looking at a cross-section of the rings. Now, in the spring, the tree grows fast and soft. It grows a fast, soft layer. You can actually see the individual cells in the ring, okay? So it grows a fast and soft layer. In preparation for winter, it starts shedding its leaves, starts storing its sap, and it builds a hard, slow-growing, thick outer layer called the late wood. So this is the early wood and the late wood, and then it stops for the winter, and that forms a tree ring. Okay, you got me so far, right? Okay, so here we are. There's 1 year, there's another year, there's another year, and there's another year. So we're looking at 4 years growth here, four or so. Here is a tree ring from Axel Heiberg. The first thing you'll notice is there's no late wood. It's as if this tree saw no winter. It's 10 degrees from the North Pole. It's nighttime for half the year. This is a tropical tree in the Arctic which saw no winter, saw lots of water, lots of nutrients, and lots of sunlight. Even during the winter when the sun does come up there, it's only a couple of degrees above the horizon. Yet by their numbers, by the evolutionist numbers, it had the approximate brush density of a rainforest. So the sun's only coming up a couple of degrees over the horizon. These trees are shading so much of each other, they don't have enough light to grow. How on earth did this tree grow there? Secondly, there's one ring there. There's the other side of the ring. Notice that in one season, this tree grew what takes a modern tree in a temperate climate 4.5 years to grow. Unbelievable. May I suggest to you it didn't grow there? Contrary to what the evolutionary assumptions are, may I suggest to you it actually did grow in the tropics. And it was floated there by a giant flood known as the Flood of Noah. Simple. But they assume because it's sitting upright, oh, it grew there. No, I don't think it grew there. Now here's the other kicker. When you take a look at the tree rings of all the stumps in that area, they don't line up. There's a whole science surrounding this called Dendrochronology, where they look at the tree rings and they can actually tell, because say for instance, if it's a dry season, all the rings of all the trees in that area will grow a very small ring because they didn't grow that much that year. And so you can actually map out the seasons and everything of the trees, but the thing is, the tree rings don't line up. They didn't grow in the same area. They were all transported there. Now, when you go to other places like Specimen Ridge and Yellowstone Park, and you have all of these fossil upright trees, these are actual fossil trees, and there's, I don't know, hundreds of them, maybe thousands. Once again, though they're buried upright, the tree rings don't line up. They were transported. They weren't buried where they grew. That's what the evidence says. Okay. The fabulous fable, fantastic fable, is that all these rock layers were laid down over long periods of time. Now, if you were here before, you caught me talking about this. This is a fossil fish from the Green River Formation, and I'll pass this around if everyone's real careful with it. It's not mine, so I can pass it around. No, I'm kidding. You'll please notice this fish has been flattened to, maybe a millimeter or two. That is evidence of rapid burial, and think about how much pressure it would take to flatten that fish. And now let's take a look at a fossil log. This is an actual tree at Joggins. Notice it's been flattened about 4 to 1 almost. It's almost 4 times as wide as it is thick. Has anybody ever tried to squish a log? I'm curious. So I'm the only weird one. Okay, that's fine. That's fine. This is good science. Hey, come on. To squish a log like that requires enormous pressure, enormous overburden. A bulldozer, a D8 bulldozer driving on top of that log would have a hard time squishing it that thin. Now, everybody agrees what squished it flat was the dirt piled on top. The thing is, in order to bury it under enough dirt to squish it that flat, you're talking thousands of feet of sediment. Now, there's enough sediment there. By the way, I forgot to mention. No, I'll come back to that later on. There's enough dirt there. That's not an issue. But the thing is, that tree has to sit there green, unfossilized, uncoalified for millions of years while thousands of feet of dirt gets piled on top of it. May I suggest to you it's the other way around. It was actually buried quickly under a mountain of dirt. Same with the fish. Where'd the fish go? Oh, there it is. Same with the fossil fish. It's very common in the fossil record. You see that throughout the whole record. There's lots of reasons to think that it will all happen quickly. Okay, and I'm going to move on to some first-hand research of mine. Again, coming back to the Joggins fossil cliffs. Now, I mentioned the calamites. There's a small one. Okay, these ones here are quite large. They're, about that big around, okay? By the way, that plant still grows today. Today, it might get about this tall. In the fossil record, it got up to the height of 2 telephone poles. Pretty much everything in the fossil record was larger than it is today. Plants especially, just got huge in the fossil record. Now, I found these calamites in the year 2003 during my study year there. And it doesn't look like much. If you can follow it, it's bent, and then it goes up vertically through the rock. Then it bends over, and it is actually bent in a spiral. Okay? There's a second one here, bent perfectly in unison with it. You see that? Okay? So it's actually bent in a clockwise ascending spiral. Sorry, I'm going to go the other way. Looking from the bottom, it would go in a counterclockwise ascending spiral. So looking from the bottom, as it goes up, it would be counterclockwise ascending. Okay? With me so far? I know it's kind of hard in the head. Now, the thing is, there they are highlighted. This was only 2 of 10 of them. And as near as I could figure, I was able to confirm at least 8 of the 10 were all bent in unison. There's the 2 I just showed you. At least 8 of the 10 were all bent in unison. And you can see little outcrops here and there. Every single one of those yellow tags marks another calamites. So here's a rough outline of a few of them. They were all bent in unison. Now the thing is, I talked to Dr. Walter T. Brown about this because I wanted to understand the physics. What happens if you take a tube? Remember, this is a hollow tube. It's just like the lycopods. It's a reed, so it's a hollow tube. What happens to a tube if you bend it? Yeah, and it kinks. That's the word I'm looking for. It kinks. These were bent without kinking. That tells us that they were supported. In other words, they had to have been buried before they were bent. So now here's the catch. There's only one time, really, they could have been bent after burial. And that's when, you remember the whole cliffs were tilted on their side? That's the only time they could have been bent. But everyone agrees all 18,000 feet of the layers were laid down before it was tipped. How long a time is it going to take to lay down 18,000 feet thick of dirt? Millions of years? I don't think so. But the plants were still green after all those layers were laid down and when they tilted. It had to have been. Now, let's move on. This was a photograph that won a competition. I'm sorry, I've forgotten the name of the guy. He was a university student at Dalhousie University. He took this photograph 2005. Now, I'm very grateful he won the competition with this because this led to a major discovery, this one photograph. I photographed this same trunk, I'm going to show you in a second, about 3 months after this photograph was taken. You'll please notice that it is cracked. See that crack in the trunk? Notice it is cracked in a clockwise, counterclockwise ascending spiral. Exact same direction as the calamites I just showed you. But this is about 3,000 feet away along the beach and about 1,000 or 2,000 feet lower in the layers, okay? Now here's the same trunk 3 months later. The front of it has fallen off because of all the erosion, and right where that split is, let's take a close look. Oh, no, let's not take a close look. Did I do it? Oh, no, I didn't show you the close look. I'm sorry. Okay. There are 2 cores of the plant. The plant has a pithy core, something like a grapefruit. And so you know how there's that very core in the grapefruit? There's two of them in this. They were also bent in a counterclockwise ascending spiral. They're actually bent exactly like the calamites. And so this is thousands of feet stratigraphically away, thousands of feet geographically away, bent in exactly the same way. If you follow that layer up, you will encounter, first of all, there's that one. About, 50 feet away is this one, right on the exact same bending planes, and it is also fractured in a counterclockwise ascending spiral. And between them, about 15 feet away from this one, is another one, which is also fractured in a counterclockwise ascending spiral. So it's like something took all these plants and twisted them. But this was after burial, and they were all bent on the same rock layers. What on earth is going on here? So I started going back and looking at my photographs. Like, okay, I saw a pattern all of a sudden. I said, wait a minute, what's going on here? Here's the layout. There's the one on the beach. That's the one that the guy took a photo of. This is about 50 feet away. And this is about, well, you can see to scale there. It's not exactly to scale, but that's roughly the layout. So you can see the mystery here. They're all fractured exactly the same on the exact same layers. But how did that happen? What caused that? Okay, so you recognize this photo I showed you right at the beginning? Let's take a closer look at this trunk. I hadn't noticed this until I took a second look. Fortunately, because this trunk was destroyed the winter after I took this picture, like I said, it's eroded constantly, so you lose everything every year. Fortunately, I took a picture from the side with my tripod in the picture for scale, so I could figure out how much rock layers it was cutting through. I'm glad I did, because that is what led me to this discovery. You'll notice it bends left, then right, then left, then right. If you look at it from the side, it bends out and in and out, in and out. It is actually buried in a giant counterclockwise ascending spiral, and if you look, there's actually still a branch in the cliffs, and that branch is actually bent coming out of the cliff in a counterclockwise ascending spiral. So all the trunks, all the branches, all the roots, the majority of them are bent in the same helical spiral. Now here's that stump again I showed you earlier. Two things to notice. Here's the root that I showed earlier, and notice it is not bent in any direction. It's perfectly straight. Here's the catch. The reason it is perfectly straight is because it doesn't go up or down in the rock layers. This root, however, you remember I pointed it out, it goes down and then back up. Notice as it goes down, it bends away from the camera. As it comes up, it bends towards the camera. It's shifting of the layers which is causing the helical spiral. The only time you see it is when a plant actually goes vertically through the rock layers, because it's the rock layers that are moving relative to each other in a counterclockwise ascending spiral, and it's bending the plants in it. That's what's going on. So, here's what this one study, it was a 5-year study I did, about 102 polystrate plants total in the study. 43 of them I couldn't really assess. They're way up in the cliffs. I mean, you got to remember, some of these are 80 feet off the ground. And I'm not about to climb these cliffs. Okay, I don't even want to stand at the bottom of them. Okay? Of the 59 which could be assessed, 29, roughly half of them, clearly exhibited some helical spiraling. That's backwards, by the way. Depends on your point of view, whether it's clockwise or counterclockwise. I did it from the bottom this time because that's usually the way you're looking, okay? So it's counterclockwise. So roughly half of them. 18 probably do exhibit a counterclockwise ascending spiral, but there wasn't enough of it exposed, or it wasn't long enough. You couldn't quite tell, but it did appear to have some. If you include that, as much as 80% of the ones I was able to study all exhibited that counterclockwise twist. 10 of them had no spiraling. There was 3 that were in the exact opposite direction. But the majority by a long shot, is twisted in the same direction. So what's going on here? What would cause that? Well, let me sum it up for you. Ooh, I don't know if we can see this. If we turn the lights off in the room, is that going to affect you? No? Except I think it's the floodlight that's washing this out. Well, let's see if we can see it. Hopefully we can. Okay, I don't think it's going to make any difference. It's that floodlight that's washing it out mostly. So we'll just, I can show you a close-up of it later. Well, that helped a little bit. Okay. Now what this is, in the bottom of the ocean, is the largest mountain range we know of on planet Earth. It's called the Mid-Oceanic Ridge. It actually wraps around the Earth like a giant seam on a baseball. But you don't see it because it's underwater. I believe it tops Mount Everest in height as well. And it's incredibly long. The mountain range here. So the mountain range, in this case, is going north to south. And across that mountain range are what we call fracture zones. There's one right there. So you've got the mountain range itself, and then perpendicular to that are all these fracture zones. Now, the hard thing to see here, an article that came out in Journal of Geodynamics a couple years ago mentioned that the fracture zones are curved. They're curved? That's kind of strange. In fact, in the northern hemisphere, they curve left. Now, here's where it's going to be really hard to see. There's a good one there. If you look carefully, it goes out and actually curves left, then curves right, and if you could see it again, it actually curves left again. But in the northern hemisphere, it curves left. At the southern hemisphere, it curves to the right. Here's one. You can see it curves to the right, then left, then right. There's another one, curving to the right, curving to the right. At the equator, they're just disturbed, is the word they looked at, the word they used. It went all over the place. The explanation is pretty simple. It's the Coriolis Effect. Now, you've all seen pictures of hurricanes from space. You notice in the northern hemisphere, they go counterclockwise. In the southern hemisphere, they go clockwise. It's the Coriolis Effect. It's caused by the rotation of the Earth. That's what causes it. Now, the thing is, if this is caused by Coriolis, what happened is these continents, there's Africa, North and South America over here, they both split at that mountain range and slid east and west of each other. Here's the catch. In order for those cracks to be affected by Coriolis forces, it has to happen at high speed. In other words, this continental division that was supposed to have taken hundreds of millions of years, nope. Days or weeks, tops. In order to have an influence from the Coriolis, it has to happen fast. It has to move at least tens of miles an hour. So you can imagine North and South America sliding west at even 20 miles an hour. And then it slams into the Mid-Oceanic Ridge in the Pacific. Gee, it's no wonder we have the Rocky Mountains. The Himalayas slammed into India, moving possibly as much as 45 miles an hour. It's no wonder we have the Himalayan mountains. No wonder at all. But as the continents shifted, apparently they also rotated. And I believe it was this rotation of the sediments that has caused this influence we see in the plants and the Joggins fossil cliffs. So that was my own little hands-on research there. And I think that's all I got for today.